Alright, welcome back. At this point in our curve sketching journey, we have spoken entirely about extrema, maximum and minimum values of a function, as well as how we can apply the first derivative test to determine the intervals upon which a function is increasing or decreasing, both using calculus concepts like the derivative or graphically. Next up we have L'Hopital's rule, because we're going to start dive a little deeper into the role of the second derivative and graphing functions that go beyond just a stereotypical polynomial. So before we actually define what L'Hopital's rule is, it is useful for, first and foremost, determining limits. And if you're a calc vet, you're like, yeah, I wish we could just do this during the limit chapter. However, it kind of defeats this purpose of like understanding, what a limit is and setting the tone or the foundation for all of calculus. Furthermore, particularly with rational functions, it helps with identifying asymptotic behavior. And if you remember back to our limits exploration, when we started to experience limits as x was approaching 0 or infinity, rational functions, we tend to run into that indeterminate form. So we'll take a little bit more of a deeper dive here in this lesson. So L'Hopital's rule says that assume that f of x and g of x are differentiable on an open interval containing, I keep forgetting this ing, a, and that f of a is equal to g of a, which is equal to 0. And why is that important? Right, because we're assuming we have a rational function here. Okay. Also assume that g prime of x does not equal 0, except possibly at a. Then you can say that the limit as x approaches a, f of x divided by g of x. So once again, we're applying L'Hopital's rule when we have a rational function. Okay, so if we substitute in this value and wind up with this 0 divided by 0 indeterminate form, L'Hopital's rule says that, well, the limit or the behavior of the rational function is also equal to the quotient of its derivatives if the limit on the right exists or is infinite. Now, we can also say, erase this, put this in a different color. So we can also say that this conclusion also holds true if f of x and g of x are differentiable. For x near but not equal to a, and limit as x approaches a of f of x is equal to positive egg infinity, and the limit as x approaches a of g of x equals positive or negative infinity. So basically, so long as we have an indeterminate form, when we are trying to evaluate the limit of a rational function, we can then apply L'Hopital's rule, which says take the derivative of the numerator, take the derivative of the denominator, resubstitute, and see what happens. And if you wind up at another indeterminate form, well, rederive and keep it moving. Let's get into a little bit of practice. See L'Hopital's rule in action. Alright, let's say we have the limit as x approaches 2 of x cubed minus 8 all over x to the 4th plus 2x minus 20. If you substitute, you'll see that we get a 0 over 0. Clearly, 2 then becomes a vertical asymptote, right? So it's determining this asymptotic behavior for us. But if we did want to know how the function was behaving, right, as it approaches 2, we would derive and derive both the numerator and denominator. So we have a limit as x approaches 2 of 3x squared over 4x cubed plus 2. Clearly, we will not, 2 times 2 is 4, that should be a 12. 8 times 4 is 32, 34, which implies 2 6/17. So we can see that the behavior of the function is approaching this value of 6/17. We can also have the limit as x approaches 0 from the right of x times the natural log of x. Once again, this is a function that you should begin to, that's what I'm looking for here, to understand its behavior or be able to recall its behavior. So we have a function that looks something like that. And if we substitute in, that should be 0 times, limit as x approaches 0 of the natural log is infinite. So we wind up with this indeterminate form. And the reason why we are evaluating this as a one-sided limit is because the limit as x approaches 0 of this function does not exist. Sorry. Because this function is not defined at that value. So, what do? Well, this is one of those situations because we don't have necessarily a rational function. We need to make this rational. How can we make this rational? Take the natural log of x, and we take this guy, place it into the denominator, which allows us to then apply L'Hopital's rule. If I derive natural log of x, I get 1 over x, and if I derive this, I get negative 1 over x squared. Which, if we simplify, gets us here. So we can see that the behavior of this function, as x is approaching 0 from the right, is going to tend towards 0. I'm going to put up one for you to practice on your own. I will also list the answer, that way you can see if you've done it correctly. We have the limit as x approaches 0 of 1 over sine x minus 1 over x. Your value there should become 0, right? So the limit of this function should tend towards 0 after you work out your magic. And we also have the limit as x approaches 0 from the right of x to the x. Whoa boy, that's a tough one. Remember when we have general exponential functions, we can rewrite them utilizing the natural log, and this turns into the problem that we just had. So we know that the value becomes 0, but little trick. So key takeaway point. Is limits involving the indeterminate forms zero to the 0, 1 to the infinity, infinity to the 0 can often be evaluated by taking a logarithm and then applying L'Hopital's. Okay, so in this instance, right, we would have 0 to the 0 power. Okay, so you can see here that we have exponential expressions that have no defined value. Hence, we would want to take first the natural log to make this exponent come down and play with the other components using arithmetic, like we had here. That's where we're going to pause because we're about to pick up and get into some real concavity using the second derivative tests and things of that nature. So see you at the next video.